So tonight we start with, or we do the lecture about galaxies. Let me open it up. This is a general overview, as you could imagine, of the types of galaxies that we find and the what the astrophysics of that actually is. And this relates also to how galaxies evolve, and that's basically the story that we're going to talk about in this lecture. Well, everything's okay. I'm recording. Oh. First, I'll talk about classification of galaxies. When you look around, you see distinctly different shapes, not only sizes, but also shapes. And that has been organized in a sense, and Edwin Hubble started with that. And I'll talk about how this evolved, this classification. And then I'll make the link to the evolution of galaxies, which is a very complicated topic. There's not very much really understood about this. But we'll link the morphology, the different shapes that we can find with the evolutionary history of what we know about galaxies. And then I'll talk about interactions, which sometimes are called collisions, but I don't use that word. Interactions or merger, I'll explain that and talk about. So what is a galaxy? I compare it, just my choice, with what is called murmurations of birds, and also it's called a fish doing that also. I just found recently a video which actually is a fantastic example of such a murmuration. So let's just start with that. I need to, as always, do some clicking in Zoom before I can find my folder from this particular lecture. I'm really sorry, this doesn't work. Why is that video not showing up? I just checked, it is definitely in that folder. Zoom has particular requirements if I want to show videos, and that's related to the fact that they have their built-in player, and if I use that according to the bandwidth and the connection, that's much better quality than when I just run a video on my own computer and show you that we are screen sharing. But I don't know why this doesn't work. Just hang on, folks. About Galaxies. Okay, I forget it. In the break, I will try to find it, but it's just a fantastic example of an actual murmuration. I think it's in an Italian city or a German city, where somebody videoed a very large flock of birds, usually sparrows or something like that, and they're not held together by gravity as galaxies are. They are held together by some fairly complex mechanism, which is that any individual bird is looking at its neighbors, what they do. And there's a strong correlation between what that particular bird is doing and the neighboring birds around it. And these neighboring birds, they're correlated with the motions of their neighbors. So this is an in statistics, you would say it's a correlation effect which spreads out throughout the whole population. It would be very complex to even program that mathematically, although they do this now with drones, I think, in some way. But anyway, let's not get carried away. I just want to make that connection. But in the real world of galaxies, it is, of course, gravity which is holding stars together. We have looked at our Milky Way galaxy. I showed you that stars are orbiting in general in one direction around a common center. But that's a very complex gravity field, but it's because it's built up not of, like in our solar system, one sun, which is almost 99% of the whole mass of the solar system. So that's very dominant. So the planets in our solar system, they just follow an orbit around the sun, as we call it. But if you have so many stars that jointly set up this whole gravitational field, and these motions become much and much more complex. But in galaxies, in our galaxy, the general trend is that stars are moving in more or less in a plane. That's why you have disk galaxies, and they are orbiting generally in the same direction. I gave you examples of stars that we found that move in the opposite direction, which is an indication that there was a merger. You remember that hopefully from the previous course. Anyway, so we have that background. Now we talk about galaxies in general, and it's the same thing. Galaxies are collections of stars, at least millions, let's say hundreds of millions, up to many billions of stars. I also talked last course about how we estimate how many stars there are in our Milky Way galaxy. You have ways to estimate the total mass of the galaxy, and then you take the average mass of a star, and then you divide it till you get an estimate for the number. Some people say we have 100,000 stars. Some people say we have, 100 billion stars. Some say, I take this back because these numbers are getting really confusing. Some people say that we have 100 million stars in our galaxy, and some other people say we have 400 billion stars in the galaxy, and that indicates how the uncertainty is of such estimates. But there are much larger galaxies which have many more stars, and then you are talking about billions of stars. And they all are gravitationally bound to the collection in an extremely complex way in terms of the Newton's laws of gravity. It is the basic Newton's law of gravity, but it is very complex because you have so many objects that all have mass and that all have an influence of the whole population. Okay, so that's the general idea about galaxies. And of course, they're not static. We have the impression, I have repeatedly mentioned that we have the idea, if we look up in the sky, that everything is immovable, it doesn't change even over a human lifespan often. But as you know now, everything moves, and also in this context, the galaxy, that is a very dynamic process that's ongoing. But because the distance is so far from us, we cannot see changes within a reasonable amount of time, reasonable being within a human lifespan or something. Anyway, so we know that the universe is very dynamic, and this is just one aspect of it. We talked about clusters of galaxies last week, and they are all moving. These are galaxies that are moving in a gravitational effect of each other in a cluster or in a group. So that's all what's happening in the universe. Nothing is ever static. Everything's moving. But now we talk about galaxies in themselves, and they are collections of stars that are bound together because of gravity in a very dynamic way. And we see various shapes. If we look around, we have nice disk shapes. We see spiral structure like we have in our Milky Way. We see a complete absence of spiral structure. We see more bulky galaxies that are not really flat. And we see very irregular shapes as well. And from the outset, early last century, astronomers have been trying to make sense of these various shapes and try to figure out what the reason is for those shapes and what it tells us about what's going on. A new estimate which I found about the universe as a whole, the observable universe, that we could have something like 1 trillion galaxies in the entire universe. Gives you an idea, or that we are not alone in our little blue planet. So let's talk about classification. It was again Edwin Hubble who first, I think he was the first. Generally, that's recognized that in 1926 he published a paper about where he tried to make sense about the morphology, the different shapes that he found when he was looking around. And he was even calling them nebulae. He didn't specifically use the term galaxy. That was a bit early. I mentioned that history, and I'll come back to that before. About that, it was only in around that time that we figured out that there are other galaxies besides our Milky Way. So what he did is he tried to make some sense of the structure in an orderly way. Very often this is interpreted as an evolutionary scheme, that you start here with what is called E0, E0, and then you evolve, and then you either branch in this way or that way, so that these are old type galaxies and these are young type galaxies. It's absolutely not correct. This is not an evolutionary scheme. It's just a morphological scheme, just trying to organize the different shapes that he found. These are what he called elliptical, and then there was a form of spiral, and he identified two types of two classes of spiral galaxies. One were normal spirals, whatever you mean with that, but then he found several of these exceptionally barred spiral galaxies. Maybe he looked around it was maybe the Virgo cluster, or maybe in another stage last week when I took you through the universe. I showed you at least one example of an extremely barred galaxy. So he came up, he realized that it was definitely a different type, a different shape that needed to be somehow organized in a collection of states, basically a morphological scheme, as you would call it. And that's why he branched to two different types of spiral. He also came with the idea of the code IRR for irregular, something that was so oddly shaped that it didn't fit into the scheme. But then there was a further evolution with contributions, of course, of many other astronomers over time. And the main classes that we have at the moment are elliptical, lenticular, spiral, barred spiral, and irregular. You see the different codes here, and the numbers mean that there's a range here of ellipticity, if you want to call it in this case, or the type of lenticular galaxies. It's and this is one of it has a bar in as well, etc. So there are subdivisions within these five main categories. This is a very interesting image because it follows the tuning fork idea, but it gives like 3 lines in each of these branches, so it's more detailed, far more detailed than Hubble originally did. But these are images, actual observations, photographs of galaxies that are particularly belonging to that type. In the handout, you can find a link to the original diagram. It's much larger. And in the handout, I also have made links to any of these particular types of galaxies. So you can click in the handout, you can click on any of those. I'll discuss these classes. And you can find a typical example there of an actual galaxy that fits in that particular part of the classification. I'm not going to do that here. That would be getting boring. But if you're interested, then definitely go to the handout. There's a guy called de Vaucouleurs in France who made an extension because he noted in spiral galaxies and sometimes in sort of a ring structure. There are two examples here of actual observations. And he put those in as an intermediate class between the spirals. So it was basically a modification of Hubble's tuning fork scheme. And then Spitzer had that was a very significant and successful infrared space telescope. Observed many galaxies, and somebody put this chart together, which is a very large scale. You can download in a really poster size version of it if you're interested. And they are organized basically in the same way of the tuning fork of Hubble's tuning fork diagram. And then, because of our observation technique improved over time, we could study those shapes in more and more detail. And a very important addition, of course, is when we went multi-wavelength. When we I have my microphone actually clipped on. I'm sorry, you may have not been able to hear me very clearly. That when you observe these galaxies in different wavelengths, you will see different features, morphological features. This here is an example. This is one galaxy called NGC 1512. It's just observed in different wavelengths. Here's infrared, and then you go to the ultraviolet, and this is the visible light version. So multi-wavelength astronomy has really contributed very much to this classification. Actually, it has made it much more complicated. It is not, you cannot really maintain such a simplistic, more or less simplistic tuning fork diagram. It's really far more complex. Every galaxy is almost its own unique shape. Of course, there are very important general classes. I'm not denying that, and we'll go into that. But especially when it relates to the evolution of galaxies. But there are so many different forms, and you cannot, it's not an exact science. That's essentially what I wanted to say. You can always say, well, this is elliptical glass, so-and-so, or do I see a little bit of a dust lane, then it may be a lenticular one, da-da-da. So it's not an exact science. But I'll go into the evolution part, and that is, of course, the important astrophysical discussion, that we learn something or try to learn something about how galaxies form and how they evolve over time. So let's summarize the main types, those 5 main types that I mentioned. First, the elliptical ones. A very famous example we already talked about is M87. If you recall last week, I mentioned and I showed you a diagram of the Virgo cluster, which is our next door. If you have the local group in the center, then next door you have the Virgo cluster. Right in the center of that Virgo cluster, there's M87. It's a typical elliptical galaxy. There's not very much shape you can see. If you would, this is a Hubble image. It's basically, obviously, often it is not a flat disk. It's more even up to spherical, or in between it would be more like a rugby ball, some sort of a 3-dimensional ellipsoidal shape. The other clear distinction with other types of galaxies is that there is no star formation happening. These are all old stars. They just live their life for as long as it lasts, and that's it. There's no new star formation happening. The reason for that is that there is no material anymore, dust and gas, out of which stars form, like in a spiral galaxy. So you can understand immediately that an an elliptical galaxy is actually, in the evolutionary sense, an end stage of galaxies. They were the first in the tuning fork of Hubble, but now we already see that because there's no star formation happening, that must have happened before, but it's run out. So this is an end stage. I'll come back to that. They come in all kinds of sizes. I showed you already some dwarfs when we talked about some dwarf galaxies of the even previous course about the Milky Way, but also dwarfs of the Andromeda, which you talked about yesterday or last week. So they come in all kinds of sizes, but it's basically an evolutionary stage. It's a final stage where there is no star formation happening. Very often there's a supermassive black hole, at least one, in the center. M87 is so famous because it has an enormous supermassive black hole. It's one of the largest that we have ever found. This is why the Event Horizon Telescope put some effort, a major effort in making an image, creating an image of that supermassive black hole. That's the famous image of the supermassive black hole of M87. You see the beam radiating out. So this is the rotation axis of that supermassive black hole in the center. There must be a jet on the other side as well. So, and very often in general, elliptical galaxies have a supermassive black hole in the center. And because it is a final stage, it will very often be the result of different mergers over time. Smaller galaxies that merged and that created a larger galaxy, and then the star formation ran out because the fuel tank was empty. There was no dust and gas anymore, and so it became then an elliptical galaxy. So that's basically the story. I'll show you a little movie about an astrophysicist. She explains very clearly how they study a particular galaxy M59 in this particular case. That gives you a good impression on how astrophysicists are studying these galaxies. I'll have this window open so I can start it straight away.
Today's Messier object of choice is Messier 59. So there's a beautiful picture that came out this year from the Hubble Space Telescope of this galaxy. I've got a printout here, but the online version is much, much better because you can pan and zoom through this image and see not only the galaxy, but the truth of whenever you point the Hubble Space Telescope at any patch of sky, all the little random background spirals and other galaxies that you can see in the background. It's a galaxy that happens to be part of the Virgo cluster, a cluster of galaxies near to our own. At first glance, it doesn't look very special. Like many galaxies in the Virgo cluster, it's an elliptical galaxy. It's a little bit bigger than our own galaxy, the Milky Way. And so what I want to talk about is the kind of detective work that we do as astronomers to learn about the physical nature of an object like this and its past history. So the first thing that we can do with a galaxy like this is to look at what we call the surface brightness profile. That just says, as we look at different parts of the image, how does the brightness in each pixel change? And can we put that all together and make a model of what the galaxy should look like? So the simplest model in this case is some sort of elliptical model, something that's brighter in the center and that falls out the further away you go. A more interesting step is to then take away that smooth profile. And we can do this because these are all digital images. So if we have a model, we just subtract that bit off and see what's left. In a paper using earlier observations from the Hubble Space Telescope, that's what these authors did. So our galaxy, Messier 59, NGC 4621, is this galaxy here. First of all, this is zooming in right to the center of the galaxy. But once we take that simple elliptical profile away, you can see the light that's left underneath. There's a very bright core, and the light that's left is the isophotes. These lines of constant brightness are quite pointed. And what this is telling us is there's another component, a physical component to this galaxy, that's not elliptical, but is more like a disk. Now we bring in what we know about the physics of galaxy formation. And we know that for elliptical galaxies, the stars in those galaxies are orbiting fairly randomly. The orbit of each star is not connected to the orbit of the other, which makes this sort of overall elliptical shape. In a galaxy like our own Milky Way, which is a spiral galaxy, it's quite flat and there's ordered rotation. The stars are orbiting along the same plane, and so the galaxy itself, we say, is rotationally supported. So what it looks like is happening in this galaxy is, although the outskirts is a nice elliptical, when you peer down into the center, you've got a component of stars, a population of stars that are actually rotating in a disk. Well, at least that's our hypothesis. How do we confirm that? Well, we need to go then from the photometry, the brightness of the object, to something that actually tells us about the motion of the stars. And this is where we take our photons, we split them up into the rainbow, and we looked at the spectrum. We do spectroscopy of the galaxy. The reason we do this is that the light coming from the stars in each part of the galaxy will be giving off sort of fingerprints within the spectrum of different elements in those stars. We know very precisely from laboratory experiments the wavelengths we expect those fingerprints to be at. And so if we observe them at a different wavelength, we know that that's telling us that there's some motion involved that we can trace. Now, the galaxies themselves, the universe itself is expanding, so we have to take out that motion. But what's left is to look at how the wavelength of those spectral fingerprints varies across the galaxy, and then we can learn about the internal rotation or orbital motions of the stars in the galaxy. And that's a pretty amazing thing. If you build a spectrograph and you look right in the central 60 parsecs, you find something unusual. There's a population of stars crammed into that region that are actually rotating in the opposite direction. So this galaxy has what we call a counter-rotating core. So you've got one component of the galaxy going in one direction, and you've got this little component in the middle plowing through in exactly the opposite direction. So it's elliptical, it's got a disky element. In the very center, it's got a counter-rotating core, and in the center of that, which we think almost all large galaxies have, it has a supermassive black hole, about 200 billion times the mass of our sun. So when we talk about parts of the galaxy, populations of stars within the galaxy that are distinct, that are decoupled from the motions of all the other populations of stars in the galaxy, one hypothesis that we have is that this is due to some past merging event. We think that galaxies, by and large, are built up by hierarchical merging, so little things merge together to form big things swallow up little things. And so this is probably a signature that at some point in the past history of this galaxy, there's been some sort of encounter. It's hard to say whether it was a major merger, a minor merger of something small, but essentially it's all detective work. And these are all the different elements that we pull together to try to figure out the history of this galaxy as we observe it here and now.
Closest to the sun, we're going to have Mercury.
Okay. Yeah, there's several things. I really recommend that you click on this link in your own time and you re-listen to that lady, because she is saying a lot of things about what she calls detective work of how they study, in this case, a particular elliptical galaxy, and what kind of information they get out of it. Again, also in the context of the evolution, that there is a distinct, what she mentioned, that stars rotating in the center in an opposite direction than in the outskirts. And this can only happen that there has been a merger of at least two different galaxies in which they were rotating in opposite directions and then they merged. But she talks about a lot of details. One thing I want to pick up here is, and it's a general concept which we must understand, is that the reason that elliptical galaxies have this shape, like what I call here rugby ball, or maybe even more spherical, is because these are orbits of stars and they have all kinds of different inclinations. the sum of all these different orbits, that's what makes the shape of a galaxy. If we look at our Milky Way galaxy, these orbits are more or less in the same plane, and that's why it's a disk galaxy. But if the orbits are more inclined in kind of arbitrary directions, then you get a more elliptical or more spherical shape if you look at the galaxy as a whole. That's one thing that she mentioned. So what you see here is, and this is a very typical example of a very massive elliptical galaxy, that this has a range of orbits of stars in all kinds of inclinations. I'll come back to the question by David. It is really a good question. M87, and I mentioned already, because there is no star formation happening, that this is an old galaxy. This is a late stage of a galaxy. It has run out of material to form stars. And if you think about supergiant stars versus, on the other extreme, red dwarfs, then the really giant stars, they live only millions of years and they go supernova and that's it. They become black holes, stellar black holes or neutron stars, but they don't live more than a few million years or maybe 100 million years on an astronomical scale of the lifetime of this of such a galaxy that is very very early. So there are no supermassive or supergiant stars in an elliptical galaxies. This is why I say predominantly low mass stars, because those are the only ones that have lived long enough to still be there. It's a very good question. I haven't thought about this in detail before, but you would expect that there are many black holes and neutron stars in an elliptical galaxies. So these are the end results of those early stage, very massive stars. So yeah, thanks. That's a very good question. It really got me to think about how to look at this, but it's really the lifetime of stars. That's really compared to the lifetime of the whole galaxy. That's really the answer. So by all means, go back to this lady. It's a really very informative short lecture that she gives about the detective work that they do to study just one particular elliptical galaxy. As an example, of course, they do this in general. Okay, so this is basically the summary of what is called elliptical galaxies. Then we go to the spiral galaxies. We know a lot about it because we have talked about our Milky Way galaxy, and our Milky Way galaxy is a spiral galaxy. I've shown you the pinwheel M101, which is not only a very good example of a spiral galaxy, but we see it face on, so you can study it in a fantastic detail. You see those arms, see the dust lanes. In these arms, there is star formation happening. That's because of a density wave that is going through the disk. You remember the course, the previous course on the Milky Way. I explained what spiral arms are. They are not fixed features. They are density waves that are passing through the disk in a different speed than the stars themselves. If you don't recall this, and go back to the dynamics lecture of the Milky Way course. That's where I discussed it. So now we can do what we can't do with our own galaxies. We can look at the whole thing in great detail. So this is a school textbook example, really, of a spiral galaxy. So it has a flat disk, more or less. So the stars are all orbiting more or less in the same plane. You could say the same inclination with respect to the galactic coordinate system. As I mentioned, these spiral arms are density waves. They are not fixed features of a spiral galaxy. Otherwise, they would have wound up a long time ago. There's ongoing star formation. This is a very important difference with elliptical, which is no star formation. Here, this is where stars are born. You need to be in a spiral galaxy. That's why we are here. Our star was only born for 4.5 billion years ago, roughly, only. And that's why we are here. In elliptical galaxies, I don't think you will find planets with intelligent civilizations on it. That's another story. I don't want to open a can of worms, but just think about it. So there's ongoing star formation. And so that means that you have lots of younger stars. That's really the point I want to stress. There's a central bulge that could be like a bar shape, but it could also be spherical. This is a very small bar, I would say. And the bar can have different sizes. It can be very extreme and it can be basically non-existent. That's what Edwin Hubble already noted in his tuning fork scheme. Then we have what is called lenticular. That's kind of an in-between situation between spirals and elliptical. It is more or less a flattened disk. That's why you don't call it an elliptical. But there's generally no spiral structure to be seen. In this case, it's a very, very famous example, 4866, of what is called a lenticular galaxy. But we see it on an angle, so we can't look face down. But there is no evidence in this image clearly of any spiral structure. You do see some dust lanes here, so that could still mean that there is maybe some star formation happening, but it is not in the stage that you get those density waves going through the disk region. So in my view, this is more or less an in-between stage between elliptical and between spirals. So in the order of evolution, that would be spirals and then lenticular and then evolutionary. I hope that that's correct because I wouldn't have any other explanation. So there's very little star formation happening, but there may be some. And therefore, again, mostly older stars. So that's lenticular. Lenticular, the name comes from probably lens shape. I think that's the translation of the English word. And then you have a shape or a class that is called irregular. Yeah, well, that's easy to say, but what do you mean? Basically, it's the dustbin of this whole classification scheme. If you can't classify it as elliptical or lenticular or spiral, well, then it's irregular because you can't make any sense out of the shape, just for morphological reasons. And the obvious reason for those irregular galaxies is that they are the result of ongoing mergers. It could be a merger that is just starting. It could be a merger that is in full process. It could be a merger in its end stage. But because of the tidal interaction that you then have between those two galaxies that are getting close, so the star streams in each of these galaxies start to feel the tidal effect, the gravity influence of gravity from the neighboring, from the other galaxy, and that gets worse when they get closer. That's what we call the tidal effect, and that really messes up the shape of both of these galaxies. It depends on which, if there's one very large one and a smaller one. The larger one would have less effect than the smaller one, but it's they both will be very distinctly disturbed in their shape, and that's an ongoing merger. I will come back to this phenomenon of mergers. Because of that, there is often very profuse star formation happening because you have lots of density waves happening in a chaotic manner, or in streams, in what we call antenna. I'll come back to that when we talk about some examples of mergers, where there's so much material being disturbed that you have lots of locations where the gas and dust falls in on itself and it forms stars. So you have an excessive amount of star formation happening, or at least a profuse amount of star formation. In an extreme case, it's called starburst. I will come back to that. And what we see, again, this is dynamics, but on a very long time scale. So we just see one stage. And it's very interesting to figure out what that stage is and how it started and how it will end. I'll come back to that as well. There's a very nice animation video I'll show you about the theory, the mathematical, the computer modeling and actual photographs of irregular galaxies. So in general, irregular galaxies are basically ongoing mergers. This is a famous example. It's the NGC 1427A, whatever that means. It's a National General Catalog. I may have shown you this because we talked about the Fornax cluster, which is in the larger Virgo cluster, aka the Laniakea cluster that we talked about last week. Fornax is actually two parts of a cluster in an extreme direction, or in the outskirts, basically, of what we call the larger Virgo supercluster. Anyway, that's what we talked about last week. But one of them is this one here, which is a galaxy itself that is plunging into the Fornax cluster. The Fornax cluster is not very large, and the galaxy probably is a significant one. I don't know. But that's going straight through at very high speed as well, through this, at least part of the Fornax cluster. This is a famous example, like an arrow shape, because of the very high velocity involved. And sometimes you see these tidal streams coming out, again, because of tidal forces, of stars that are being flung out in very large distances from the center of their original galaxy. Reminds me that in the previous course we talked about dwarf galaxies, but also streams. I showed you that there are several streams around our own galaxy of smaller galaxies, dwarf galaxies that are merging or have been merging, in a stage of merging, and they're being stretched out. Those stars are being stretched out into streams rather than that it stays like a dwarf galaxy in its own right. And on a larger scale, you see that here when galaxies of similar size are, or any size really, but sizable galaxies are merging with each other. I talked about the Andromeda, which will merge over a long time with the Milky Way galaxy. I hope you remember that. That was, when was that? Oh, and that was that was last week or the week before. And I told you that based on new observations, especially velocity measurements, we now know that it will happen much later than initially thought. And it will be, the initial encounter will be at the distance, a mutual distance of something like 400,000 light years. So it's not directly going to be a merger. But what happens what will happen is that the two main, and these are two big galaxies, of course, they will be continuing in each other's gravitational influence. So eventually that will merge and very likely ultimately become a very large elliptical galaxy. But I also mentioned that don't lose any sleep over it, because our solar system will not exist anymore when that happens. Anyway, just going back to something that we discussed before, and that also is a merger of galaxies. And this is happening everywhere and all the time. So let's now look at the evolutionary aspect. So I emphasize again that this is not an evolutionary diagram. There's no time scale horizontally. If there were a time scale, it would be in the opposite direction, because the ellipticals, they are the oldest one. But it's not really a time scale at all. But in order to explain these different shapes and sizes, we need to do astrophysics, like I already discussed, and I showed you that lady who was explaining how she studies one particular galaxy in detail. We also must remember that we are always looking back in time. So because our telescopes are time machines, so we can look at early galaxies in the early universe even, and we can look at closer by, which are galaxies that are more or less in our time frame in astronomical sense. And if you combine that, you can also reconstruct an evolutionary aspect to it. So that's basically the whole very difficult, very complex study of galactic evolution. So here I emphasize that there are, in terms of star formation, there are basically two types. The ones that have ongoing star formation, and they are typically the spiral galaxies, and you have the ones that don't have star formation. They must have had it in the past, but they don't have it anymore. They just ran out of the material, the dust and the gas that out of which stars are formed. And the metallicity of stars, which is the amount of other elements that we find in the spectrum besides helium, hydrogen, and helium. This is what astronomers call metals. Very confusing, but that's astronomy. They have their own language. And when we go into the Big Bang model and things like that later in this course, then it will become more reasonable why they do this, why they have a special name for a separation for stars that have only hydrogen and helium, or stars that have also the other elements. There's a good reason for that, because hydrogen and helium were the first elements that formed in the early universe. And all the other elements formed in merger events, in exploding stars, in all kinds of reactions in or between stars. So you must already have star formation happening in the early universe before you get this enrichment of the periodic table. That's really the story. I mentioned this before sometime. There was a name nucleosynthesis, but I'll come back to that later in this course. So the metallicity that we observe from the different stars in such a galaxy tells a lot about how long these stars has been forming, how long they have been forming in the particular galaxy. So how much enrichment has happened over the lifetime of the galaxy. There's another aspect which is called quenching, which is the effect that there must be a mechanism with which, especially in elliptical galaxies, the gas and dust out of which stars form, so that's basically the fuel tank for star formation, is emptied in a specific way, not because stars form and go through the cycle, but that material is stolen from the galaxy in some particular way. That's what is called quenching. The reason that there must be something like that is that we find far too many elliptical galaxies. If you think about the evolution of the universe and the ages of the different galaxies, there is something that's not right, that we can only explain if there is a mechanism, or maybe more mechanisms, in which galaxies can actually lose that valuable materials, dust and gas, out of which stars form. And the main model, as far as I understand this, and I have some reference about this theory in the handout, is that if there's a supermassive black hole in the center, that can be swallowing up material, which doesn't get a chance to form stars further out in the galaxy. There's apparently just a correlation here. That's what this diagram indicates, between the mass of the black hole and the total mass of the galaxy itself. So the smaller galaxies, they are in the smaller galaxies, you have supermassive black holes that are larger if you increase the size of the galaxy. This is a very complex process. I'm not going to explain this in any detail. I couldn't. I would have to read up more detail. If you're interested, I have a link in the handout about this quenching theory. So let's look at this concept called merger. Many people, even astronomers, talk about collisions. I'm really preventing to use that word because it's not, doesn't make sense. When we talk about collision, we think about something that physically collides, and there's nothing colliding physically. These are mergers. The reason is that even if in a dense spiral arm of a galaxy, the mutual distance between neighboring stars is extreme compared to the size of the stars. We talked about it even in the very first course, solar system, a sense of scale. I gave you a scale model that our sun is a pinhead, and then the nearby star, and the closest stars that we have is Alpha Centauri system, is in that scale model where the sun is a pinhead, is 40 kilometers away. And those are two pinheads and a very small red dwarf, which is much smaller than a pinhead. That's the scale model of our sun and the nearest star. So, and I extrapolated from that the average mutual distance between stars in our neighborhood in the spiral arm of our galaxy, which is a dense region, is something in the order of 60 kilometers in that scale. So you have a collection of pinheads all over the place, but you need to, from one pinhead to the next, you need to travel 60 kilometers. So this gives you an idea about the emptiness. That was my conclusion, the emptiness of the universe. So if we now look at it at the galactic scale, we think about, oh, a spiral arm, that's a really dense collection of stars. Well, on that scale, yeah, but if you zoom in, you see that it's almost empty space. And therefore, even if galaxies would collide head on, stars would basically they would hardly notice each other. I mean, visually. The gravitational effect will be there. That's the tidal effect, the tidal forces. That's why you get the deformation. But there is nothing like a physical encounter or collision between stars. In worst case, stars could start orbiting each other, or they become multiple systems or something like that. Here you see an image of an ongoing merger, and you can understand why people call it an irregular galaxy. And if you study this, and especially velocities in detail, but also age and all kinds of information that you can extract from spectra from these stars, then astrophysicists can kind of reconstruct the history of that merger. So where are we in that merger? This looks to me as a layperson like a merger maybe in its central moment, when they really go through each other. Because of the shock waves, I mentioned that before, the density waves, there is a lot of star formation happening suddenly. If these galaxies have still enough dust and gas out of which stars form, because of all the compression that is happening, you get a much larger amount of star formation than in these individual galaxies beforehand. And if one of them is an elliptical galaxy, then there was no star formation at all. But if the other one is a spiral, then in that material of the spiral galaxy, you will have an increase of the star formation. There are often the streams. I'll show you examples of that, and I mentioned it before, but I'll show you some examples of that as well. If we if we talk about and look or think about clusters of galaxies, like for instance the Virgo cluster that I talked about last week, I mentioned that in the central region of that cluster, there are predominantly elliptical galaxies, and the spiral galaxies are more in the outskirts. So there is an age difference radially from the center of this whole cluster. This is and that has to do with the evolutionary history of the cluster itself, the whole cluster of galaxies. That the older ones end up in the center, and that the younger ones, the spiral galaxies, are more in the outskirts. So all these things are related to each other. So I hope that you get the idea that astrophysics, in terms of studying these interactions between galaxies, and also evolution of galaxies themselves, it's a fairly complex matter. I'm just giving you the kind of scratching at the surface here, kind of an overview. And then we have this term starburst, which I mentioned before, and that is an extreme amount of star formation. If we see that happening, that will be visible in the merging stage of a merger. So you have different galaxies, they interact, and then in the heyday basically of that whole event, which takes at least millions of years or hundreds of millions of years, there's an excessive amount of star formation happening in some cases, which is called a starburst. This relates to what is called active galactic nuclei, AGN. I'm not going into the difference. It is really too complex also for me. I would really have to study this. It's not really necessary if we think about this overview. But an active galactic nucleus is a galaxy that is the central region in a galaxy that has a very large supermassive black hole. And if that happens, when there is a merger between two of these galaxies, then you get an enormous amount of activity in the central region. That's called an active galactic nucleus. And then after the collision, when things settle down, you get what they call post-starburst shapes of the remaining, the combined galaxy. And the end stage could be is very likely in the elliptical galaxy. And stars have formed and they have lived their life. Only the old stars are still there, and there's nothing much happening. So that's this elliptical stage. But that's what I talked about in terms of the AGNs. Quasars has to do with it. Again, I cannot go into much detail, but quasi-stellar objects, that's where the name comes from, they were discovered in the 1950s when radio astronomy came up. Straight after the Second World War, some astronomers became interested in radio signals from space. They were discovered and they wanted to study it. Jan Oort, the Dutch radio astronomer, is one famous example. And in Jodrell Bank in the UK, there was a telescope built. Often these initial telescopes were radar antennas that were left over from the Second World War. But anyway, they started to observe radio signals from space. And at some point in the 1950s, there were objects, fairly strong radio signals were observed. But when I looked at the spectrum, the redshift was extreme. It was absolutely unbelievable. So, in other words, these must be extremely far away objects. Sometimes in that direction, there was no visible star or object. Sometimes there was a visible light source, but the radio signal was very much stronger than in any other wavelength. And because of the intensity of the radio signal, they had to conclude that if they are so far away, that they also must be very dense objects, that they must have a very small angular size, so to speak. And they got the name quasars. There are no quasars anymore in the current in the modern universe, but of course, when you look deep, then you will find those. Somehow, these quasars relate to what is called active galactic nuclei, when there are supermassive black holes, really, really supermassive black holes in the center. And maybe in a merger situation where there's an extreme amount of activity and radiation produced in the center of that merger. So that's really the point I want to make. In the handout, I will have more links to details for further study if you're interested.